Have you ever wondered how debugging tools can magically show you exactly where your program went wrong, revealing the sequence of events that led to an issue? It is not magic, it is the call stack. A debugger visualizes the call stack by interpreting the memory layout of a running program, presenting the sequence of active function calls in a clear, ordered list, typically from the most recently called function at the top, down to the initial function at the bottom. This visualization is crucial for understanding the execution path and pinpointing the exact location of a bug. The core mechanism behind this visualization lies in how programs manage function calls in memory. Each time a function is called, a dedicated block of memory, known as a stack frame or activation record, is pushed onto the program's call stack. This stack frame holds essential information for that specific function call, including its local variables, arguments passed to it, and the return address. The return address tells the program where to resume execution once the current function completes. The debugger reads these stack frames, reconstructing the chain of function calls. Think of it like a stack of plates, where each plate represents a function, and the top plate is the one currently in use. When you use a debugger, for example, by setting a breakpoint, the program execution pauses at that specific point. At this moment, the debugger inspects the memory associated with the call stack. It then parses the information from each stack frame, extracting function names, line numbers, and parameters, and presents them in a user interface. This allows you to walk through the call history step by step, examining the state of variables at each level of the stack to understand how the program arrived at its current state. You can click on different stack frames to see the source code and local variables relevant to that particular function call. An interesting detail is how the program counter, or PC, plays a role. The PC is a special register in the central processing unit, or CPU, that always points to the next instruction to be executed. As stack frames are pushed and popped, the return addresses within these frames guide the PC, ensuring the program returns to the correct place. Debuggers leverage this by mapping the return address within a stack frame to its corresponding source code location. Another key component is the frame pointer, or FP, which is a register that helps manage the current stack frame, making it easier for the debugger to locate specific data within that frame. This intricate dance between memory management units, the central processing unit, and the debugger's logic allows for such powerful insight into program execution. Ultimately, the debugger's ability to visualize the call stack empowers you to not just see that an error occurred, but precisely asterisk how your code reached that problematic state. By tracing the flow of execution and inspecting the data at each function call, you gain a deep understanding of your program's behavior, transforming the daunting task of bug hunting into a logical, systematic investigation.
If this helps you fix faster, like, subscribe, and keep debugging with us.